All right, in quiz 2, this is the situation. We have charges on the XY plane, part of it positive, part of it negative. Lambda is given 0 to pi as lambda 0 and pi to 2 pi as negative lambda 0. So this is my separation vector. So I need to just write it out. R is ZZ hat as before, and R prime is, if I use cylindrical coordinates, basically the magnitude of R prime is constant. It's around the circle. So the position, I can just say R, say S hat. Okay. So now S hat is a variable vector. I got to be careful about that. So, but then the script R would be ZZ hat minus R S hat. Remember where I can write S hat as X hat cosine phi plus, again, this angle is say phi, and then Y hat sine phi. So now I can write the integral as dq script r divided by script r magnitude cube. So if I replace this here, and then script r magnitude obviously is pretty easy. R squared is here, c squared plus capital R squared. Right, so I can just replace that here. So it becomes 1 over 4 pi epsilon naught dq zz hat minus capital R S hat divided by z squared plus R squared, square root of that to the third power, so 3/2. Now, what is dq? Well, dq is lambda dl. In this case, dl, since it's going around the circle, r times d phi, that's the tiny little arc. So I can write dq as lambda r d phi. Well, obviously, the integration will happen 0 to 2 pi, and I can write 1 over 4 pi epsilon naught integral phi equals 0 to 2 pi lambda r d phi zz hat minus r s hat z squared plus r squared 3/2. Now here 0 to pi I need to use lambda naught, and pi to 2 pi I need to use minus lambda naught, and I have z hat component and s hat component, so I need to do 4 separate cases. Okay, but I should realize, I mean, this is a constant, z is a constant, r is a constant. I mean, constant in the sense that it's not an integration variable. So lambda r, lambda naught also a constant. So they are all, they can be taken out of the integral. So that's what I'm going to do as I'm writing this out. So let me just go here and then write all the terms along the line. So what we have is 1 over 4 pi epsilon naught. Okay, z hat is constant, so I can just pull it out. R z hat over z squared plus r squared 3/2. Okay, this is for the z hat part. And then I have phi 0 to pi, and then this lambda, because plus lambda 0 d phi, and then plus phi pi to 2 pi minus lambda 0 d phi. That's the z hat component. Now plus, now the s hat component minus r part. Now r times r is minus r squared. So let me write that out. So it's going to be 1 over 4 pi epsilon naught. Again, you have minus r squared here, minus r squared, and divided by c squared plus r squared 3/2. okay? And then I have phi 0 to 2 pi lambda d phi s hat. Now, I'm not taking this out because this is not constant. I need to write this in terms of x hat cosine phi, y hat sine phi when I do that integration. Now, but one thing we can notice here is that this integral and this integral, they cancel each other out because this is 0 to pi d phi. The result is just pi. This is pi to 2 pi d phi, that's also pi, but there's a negative sign and then lambda knots are equal. So this is going to give me nothing. So this is 0. So there's no z component. So the actual part that I worry about is this. Okay, this integral I should take. So I can just say, all right, let me call that capital I. And capital I would be, okay, phi 0 to 2 pi lambda x hat cosine phi plus y hat sine phi d phi. Okay. That's the integral I need to take. And again, this will be separated into two parts. So I have phi 0 to pi x hat cosine phi plus y hat sine phi d phi, and that's going to be plus lambda 0, and then minus lambda 0 phi pi to 2 pi, and then x hat cosine phi plus y hat sine phi d phi. Now, here, the essential integral I need to worry about is the cosine phi d phi, evaluated at pi to 0, and then sine phi d phi evaluated for the same range. So cosine phi, when you integrate, it's going to be sine phi, and then at pi and 0, and at pi and 2 pi, that always gives me 0 because sine of pi is 0, sine of 0 is 0. So there is nothing coming from these parts. Okay, those parts. Okay, I know. So that means the net field will be always in the y hat direction. So if I rewrite this, lambda naught y hat, and then I have phi 0 to pi sine phi d phi, okay, minus phi pi to 2 pi sine phi d phi. Okay, so let's evaluate this. So this is cosine phi lambda naught y hat, negative cosine phi evaluated 0 to pi, and that's negative cosine phi. There's another negative, so that's plus cosine phi evaluated at pi and 2 pi, right? So let's write it out. So my I integral will be lambda naught phi hat, okay, minus cosine pi minus cosine 0. I'm just doing explicitly just to show, plus cosine 2 pi minus cosine pi. Okay, you can more easily just straightforwardly say this, but lambda naught phi y hat, this is minus 1, this is plus 1. Okay, minus 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 2. And this is 1. This is negative 1. That's going to give me plus 2. So this is going to give me plus 2. So the result will be plus 4, all of them all together. So I need to now take this and plug it back into the equation. Now, when I plug it back into the equation, this is what I get, because that's the function that multiplies the integral I just completed, and I get this. Okay, is this reasonable? One thing you can do is just the dimensionality analysis. Well, linear charge density, Q over L, R squared is length squared. This is length cubed. You look at it, Q over L squared. So 1 over 4 pi epsilon naught, some charge over length squared. That seems to be right for the dimensionality. So the other thing is the vector direction reasonable, right? So in order to analyze that, you can look at the symmetry situation. And for example, if I look at the YZ sort of, there is a, with respect to the plane parallel to the Z, there is a symmetry. So on this side, on the first and second quadrant, I have positive charges. On the other side, on the left here, I have negative charges. So if you take any point on the Z-axis, due to the positive charges, I have an electric field like this, and the negative charges, I have an electric field like this. And you see their components, Z components will cancel out. That's one thing. Second thing is, there's also a symmetry with respect to the Y-axis, because now if you can look at, this is X, say this is Y, okay, and this is the positive charges, okay? So let's look at the origin, right? It's easy to see. So if I have a positive charge here, there is a positive charge right on the other side, symmetric with respect to Z-axis, and the contribution of this one pointing away, and this one is also pointing away. Or you can think of it, any projection of the vectors on the Z-axis on the XY plane, that's going to generate these kind of vectors. So as you see here, the X components cancel out, and the negative Y components, the components in negative Y direction, add up. If you do that for the negative charges, you'll get something similar, because here, again, these vectors will point in the same direction, and their X components will cancel out. So we expect only negative Y, the net electric field, to be in the negative Y direction. I hope you enjoyed the solution.